All right, so we're looking at section 4.1 here. We're going to look at exponential functions. Here, our basic exponential function is going to be of this form here. F of x equals b to the x, where b is called the base of the exponential function there, and where b is a positive, it's a positive number, just like that. All right, so it's going to be a positive number. It's not going to be a negative number. It can be a fraction, but it's going to be a positive number. And x is going to be any other real number. It's our variable. So the thing that's different about this compared to what we were doing before is we have this x now. This is our variable that's actually up in the exponent. Before we did stuff where we had the x that was down as the base, and then we had some fixed exponent like x to the fifth or something like that, where the base was the variable and the exponent was a constant. Well, now we're switching it around so that the base is a constant and the exponent is the variable. So we're going to try a couple of these here. It says determine whether each of the following equations is an exponential function. If so, identify the base. Look at this first one here. This is an exponential function. We have a base b equals 2, and it's a positive number, right? And so therefore, yes, this is exponential. All right. If we look at the next one here, we have a base equal to 1. It is a positive number, so yes, this is exponential. We go to this next one, and you look at it, and maybe it doesn't quite look like this form, just b to the x. But that's okay, because essentially what that is a horizontal shift, just like all of our previous functions. If we said f of x equals 5 to the x, then we can say this is f of x minus 1. And so that's a horizontal shift for us. So yes, here we have a base equal to 5, and we just happen to have a horizontal shift. So it's going to still be the same exponential function. All right, so I'm going to go ahead and pause there, and I want you to think about the next 3 of them and decide if you think they are exponentials or not, and then what their bases are, and then we'll keep going after I give you all a minute to do it. All right, so taking a look at the next ones, we have -2, and then it's to the x power. This one is going to not be, it's not exponential. The reason for this is because, well, one, that base is a -2, and it's not a positive number. And so that kind of does it for us. But if you think about this one, what's going to happen is it's going to kind of jump all over the place. And when we see the graphs of what exponential functions look like in a bit, it's not going to fit it at all, because if you go -2 to the first, you get a negative number, -2. If you go -2 to the second, you get a positive number. If you go -2 to the third, it goes back to negative. And to the fourth, it's back to positive. So this one's kind of all over the place, and it's not going to be, it's not going to fit this exponential type of shape and graph that we're doing here at all. Number 5, this one actually is going to be exponential. So you need to pay very close attention to the difference between 4 and 5. I can actually write number 5 this way. It's the negative of 2 to the x, like that. And so that's actually just going to be a vertical flip with that negative sign out in front. So it's not going to change the shape of our graph. It's going to be like a 2 to the x graph, just flipped over vertically over the x-axis. And then the last one is x squared. Oh wait, so this one is exponential, and this one is not exponential. That one, the base is the variable and the exponent is a constant, so that's not our exponential function there. Okay, next part here, you can just see some of the applications of this that might come up. They're used a lot in a lot of different areas: economics growth, environmentalist, population growth, decay, countries of different animal species. You probably saw this one, growth of epidemics or pandemics, has probably seen that charts of these and how it's looked like that. Chemistry, physics, stuff like that. It's used in radioactive decay and growth and half-life. It's used a lot in medicine. It's comes up a lot in that kind of stuff. It's banking businesses. It's used for interest. In fact, A base of E, Euler's number, is used. In fact, it originally comes from essentially a way to compound investments continuously, where you do it all the time. You end up getting that Euler's number E, the base of the natural logarithm. You end up getting that from there. All right. On the next page here, we're going to go ahead and try just doing a couple of these, and we're going to just pick out points and go through and see if we can get what this graph is supposed to look like. So this side we'll put x, over here will be f of x. So we're going to start by picking one of the most common points, and that's 0. If we pick 0, we end up with f of 0, and that's 2 to the 0, and anything to the 0 power is just 1. So we'll get the point 0, 1. And in fact, no matter what the base is, assuming we're not having any shifts or flips or anything going on, it's going to go through that point 0, 1. All of our graphs are going to go through that point, assuming we don't shift it or flip it over away from that point. But any just basic exponential is going to go through that point, because no matter what the base is, if it was 10 to the x, we'd plug in 0, it'd be 10 to the 0, and we'd get the point 0, 1 again. It would just be 1. So no matter what the base is, it's pretty much going to go through that point. So that's a very good one to remember for these graphs. Next, another point that's pretty good is if we plug in the number 1, we get f of 1. This is 2 to the 1 and just 2. So the point 1 and then to the base, 1, 2. We have a base of 2 here, right? B equals 2. So 1, 2 is also going to be a point. Next, we could try another point. Let's try 2. F of 2 is 2 to the 2, which is 4. So we have the point 2, 4. Then we can try 3. F of 3 is 2 to the 3, and that's 2 times 2 times 2. That's 8. And so that brings us way up here at 8. And you could keep going. You could go 2 to the 4th. That would be 16. You're going to be like way up here. And then 2 to the 5th would be 32. And we're up off the top of the page there. So it's going to actually go. And on the positive side, it's essentially just going to blow up real fast and get real vertical and start, well, not actually too vertical, but it's going to get going up really, really fast, faster than it moves to the side. So it'll get very, very steep. All right, next we need to look at what happens when we get on the negative side. So let's start by looking at -1. So if we do f of -1, we end up with 2 to the -1. And the way we deal with negative exponents is to essentially get rid of the negative and then take the reciprocal. So instead of 2 to the 1, we do 1 over 2 to the 1. Just like that, we get rid of that negative sign, do the reciprocal, and this is just 1/2. So if we come over here on our graph, then we have to come over here to -1, 1/2, just like that. Then if we come over here and we try -2, we get f of -2. That's 2 to the -2. That's 1 over 2 to the 2. That's 1 over 4. So down here, if we go to -3, we get f of -3. That's 2 to the -3. That's 1 over 2 to the 3. That's 1 over 8. And so we're getting really close to 0 there. And in fact, as we keep going more and more negative, we're going to keep ending up putting larger and larger numbers on that denominator. And the larger the numbers in the denominator get, the smaller our total number is. And it's going to start to asymptote down to 0. It's going to get close to 0, but never actually reach it or go below it. So that's what our exponential graph is going to look like. That is our basic exponential graph. So I'm going to pause real quick and check for any questions before we go on with the next one. All right, so after looking at that one, we're going to go down here and take a look at g of x to the 1, or g of x equals 1/2 to the x. And so we're going to go ahead and try this one. We'll make ourselves a chart again, x and, well, this time it's g of x, not f of x. So g of x. And so we'll start with our regular old 0. So at 0, we get g of 0. We get 1/2 to the 0, which is again just 1. So again, we have that point 0, 1 right there. We're going right through it. We can now try the point 1. Before, when we plugged in 1, we just got the point. We got 1 and then whatever the base was. The base is 1/2 here. So if we do g of 1, we're just getting 1/2 to the first power, which is 1/2. So 1/2 is our point right there. And that's, of course, because b equals 1/2. So two quick little points to get you going right there. We can try 2. We'll get g of 2 equals 1/2 squared. So that's 1/2 times 1/2, that's 1/4. So we're getting down here to 1/4. If we go to 3, we get g of 3. That's 1/2 to the third. That's 1/2 times 1/2 times 1/2, that's 1/8. And so we're getting really close to 0. And as we keep getting larger and larger, we're going to keep making that denominator smaller and smaller. And so we're going to asymptote right here towards 0. Just like that. We're going to asymptote over towards 0, but never actually reach it or cross it. Now, what happens when we get to the negative number? So let's try -1 first. G of -1 is 1/2 to the -1. But like I said before, when you have something to a negative exponent, you can take the reciprocal and then just take the positive exponent. So this becomes 2 over 1 to the first power, which is just 2 to the first power, which is just 2. So we have the point -1, 2. If we go to -2, we'll see g of -2, which is 1/2 to the -2, which is just 2 to the 2, which is just 4. There we go. And then if we did -3, g of -3, that's 1/2 to the -3, which is, sorry, not 3, which is 2 to the 3, which is just 8. So we come over here and have this point. So if you notice, when you compare these two, you can see a relationship between the two of them is that, taking a look at this, they are just mirror images of each other across the x-axis. All right, and that should make some sense to you, if I give myself a little room here, because this function, 1/2 to the x, remember, I can write this like this. I can make this 2 to the -x, right? Because I can take the reciprocal and then change the sign of the exponent, all right? And 2 to the -x, that would be a horizontal flip, right? That's f of -x. That's g of -x or whatever it is, right? And so that's a horizontal flip across the x-axis or across the y-axis. And so that's what we ended up with here. So 1/2 to the x is essentially that horizontal flip. So what is the relationship between the graph of f and g? They are reflected. They are reflections across the y-axis. They are horizontally flipped. All right, let me pause and see if there are any questions for this part. All right, so let's go on the next page here. We'll look at some characteristics of this function. There you can see it done in blue there for you. The domain for this, well, we're able to plug in any numbers we want for x. So we can actually plug in any real numbers we want, all the way to negative and all the way to positive x. We can plug in whatever values we want. And so our domain here is going to be -infinity all the way to positive infinity. There's no square roots. There's nothing undefined that's going to happen. And so we're good with just that. The range, on the other hand, you can see here that we're going all the way up. We're going to go to positive infinity over there. But look over here. We never, ever get below this x-axis. We get close to it. We never even actually reach it. So we never get to y equals 0. So our range is that we can be above 0, not equal to it. So I put the parentheses. And then we can go all the way up to positive infinity, but we never get below it. Not unless we have this thing vertically shifted or something like that. But just the regular old exponential functions, they're not going to go below. There's nothing you can plug in that's going to give you a negative result or a 0 as the result or as the output. The importance of the point 0, 1, we already talked about. They all go through it unless shifted stretched or shrunk or whatever, okay? Unless we do something like that where we move the graph around or stretch it or something like that, that was supposed to be an etc. Then it's going to go through that point 0, 1. Horizontal asymptote, that is occurring at y equals 0 along the x-axis. That's where we're never getting through here. And what you can see with what we did on the previous page is if we have a base that is greater than 1, then the graph is an increasing function. If the base is a fraction between 0 and 1, then the graph is a decreasing function. And that's, again, what we saw here. B was greater than 1, it was 2. And then over here, it was less than, I'm sorry, I circled the wrong thing. It was less than 1, it was 1/2. And so we got a decreasing one. So we had an exponential growth up here and an exponential decay down here, okay? The last thing I want to point out is what's going to happen if our base equals 1. So here we talked about greater than 1, and we talked about less than 1, between 0 and 1. What happens if it's just 1? Well, if it's just 1, then it's 1 to the 0, which is 1. It's 1 to the 1, which is 1. It's 1 to the 2, which is 1. It's 1 to the 3, that's 1. It's just the constant 1. And so one of the things we need to add back over here, it's a positive number, but b does not equal 1. That's going to be a kind of a boring case for us, where it's just going to be a straight line. All right, it's just going to be a horizontal line there at y equals 1, because no matter what, it's going to come out to be 1. Okay, so I wanted to get over here before I put that in. Here you can see a few little examples of what happens here. Over here we have positive greater than 1 bases, and you can see they're exponentially growing. And the larger the bases, the faster it grows. Like here on this one, it's growing a lot faster than that one does. On the next little group here, we have fractional bases, or bases that are between 0 and 1, and you can see they're decaying, and they decay faster with the larger denominator here than they do over here. They go down and decay. All right, so those, you need to be familiar with those. All right, so I'm going to go ahead and pause here and see if there are any questions. All right, so now we're going to come over here and look at transformations. Basically, these are going to transform just like the previous graphs we have studied. We're going to just shift them vertically, horizontally. You can stretch them, shrink them, reflect them. All that kind of stuff can occur just like this. So here what we're looking at is vertical transformations, where we have essentially that whole idea that we have an f of x, we have a function plus or minus some number like that. And then that's a vertical shift. And so we have a +5 here. When we're doing something vertically, we do exactly what is there. So this will be up 5. This one here is a -5. And again, it's after the exponential. It's outside of the exponential function part itself. And so this is going to be vertical. And therefore, we're going to do exactly what's there. That's a down 5. Next, horizontal transformations, they occur when you have it acting directly on the x. And you can see here that it's happening up in the exponent like that. So it's going to be a horizontal transformation. And then when it's horizontal, you do the exact opposite of what is there. So here we have a +5. So we're going to move left 5, so in the negative direction. And then we have a -5 up here. So we're going to move right 5 in the positive direction, just like that. Okay. And then the last thing we're really interested in are reflections. And we had 2. We had the vertical reflection, which was a reflection over the x-axis. And that was when we had like a negative f of x. And then we had the horizontal, where the negative was inside the function on the x. And that was this was a reflection over the y-axis. And so if we look at that first one, the negative is out in front. And therefore, this is a vertical flip, or flip over the x-axis. The next one, the negative is inside it, in there on the x. And so this will be a horizontal flip. or a flip over the y axis, okay? And so those are our different types of transformations that we're mostly interested in. You could also do like a 5 times f of x, like like a 5 times 2 to the x, like that. You could have something like that, in which case you're going to get the vertical stretching going on. So instead of the point 0, 1, instead of it going through 0, 1, it's going to go through 0, 5, because 2 to the 0 would be 1, and it'd be times 5, so it'd go through the point 0, 5 instead. So it would just stretch it up vertically. But we're not super interested in doing that now. But if you do come across it ever, you can just do the same exact sort of thing and stretch it up vertically by 5 or whatever it is out front. And you can do the same thing if the value is up there and the exponent acting on the x, you would just stretch or shrink it horizontally. All right, so let's take a look here at f of x equals 5x. Zoom in on here. We go through the point 0, 1, and then through the point 1, 5, because our base is 5. So 0, 1, and then 1, 5. And then we can just kind of sketch this in here. It's going to go like this, and it's going to come over here and asymptote down like that. And so we have that graph right there. Now, how do we change that over to f of x equals 5 minus x? Well, you could plug numbers in if you wanted, or we can just do a horizontal flip or a flip across the y-axis. So this is flip over the y-axis. And when we do that, we still go through the point 0, 1, but instead of the point 1, 5, it now becomes negative 1, 5, like that, because we're flipping it over from the point 1, 5 to the point 1, negative 1, 5, just like that. And then it's just a matter of sketching. That was not very good. Let me try that again. It's just sketching your exponential like this. Oops, I went below the axis. So something like that. Now we have that one. The next one asks us here is 5 to the x minus 3. This is a vertical shift because it's occurring after. And so there we're going to do exactly what's there. We're going to go down 3. So our original points were 0, 1, and 1, 5. And so I'm just going to move those each down 3. 1, 2, 3, 1, 2, 3, just like that. Make those points there. But I also need to, after I move those points down, I need to move my horizontal asymptote down. So if we look over here, our horizontal asymptote was the x-axis. Same thing here, the x-axis. But now we're going to drop it down by 3. So it's actually going to be the x equals negative 3 axis. That's where our asymptote is the x equals negative 3. It's going to drop down over top of that right there. And so we're going to go just like that and come up here just like that, even though that was kind of not the best drawing of one. But anyway, there you go for that one. So go ahead and take a moment, look these over, and take a look at 12, 13, and 14 and see if you can graph those out yourselves. All right, let's take a look at these next 3 down here. So here we have 5 to the negative x. This is going to be a vertical flip or a flip over the x-axis. And so we're going to take this graph right above it, which was 5 to the x, this graph, and we're just going to flip it down like that. And so we had the points 0, 1, and 1, 5. And so we're going to flip those down to 0, negative 1, 1, negative 5, just like that. So those will be our 2 points that we're interested in. We're still going to asymptote towards 0, but we're going to do it below the x-axis this time, and then we're going to curve around like that. So it'll look something like that for our graph. Of course, try to get through the points a little better than I did. I kind of missed that one. There we go. Maybe that's better. I don't know. All right. The next one is f of x equals 5 to the x minus 3. Since that minus 3 is acting directly on the x, that means we have to move horizontally. And so we do the opposite of what is there. So instead of moving left 3 or in the negative direction 3, we're going to move in the positive direction 3, so we're going to move right 3. All right, so we take our original function, we had our points here and our point there, and we're just going to move them each to the right by 3. So instead of 0, 1, it becomes 3, 1. And instead of 1, 5, it becomes, comes to be 4, 5, not 5, 5, 4, 5, like that. And so we just move our points like that. Our asymptote stays the same. We're just going to, going to come down here, curve down, and then asymptote over to 0 like that. So something like that, where we're going to curve. We're going to curve like that, and those are our points right there and there. And then the last one, we actually have 2 transformations occurring. We are going to shift here. We're going, that's a +5, so we're going to go left 5. And we also have this vertical flip here. So this is over the x-axis. All right, so we have both of those, flipping over the x-axis and shifting left 5. So our original points are there and there. We're going to go left by 5, so that puts our points there and there. And then we're going to flip them. So that was left 5, left 5. And now what we're going to do is go down and flip it over the x-axis like that. Flip them down like that. And so we'll get the points -5, -1, and -4, -5 like that. So we just flipped them each down like that. And then that leaves our asymptote in the same place, x equals 0. And so we just have to draw in our curve here, which is something like that. Okay, except hopefully a little better than I just did that. Okay, so something like that. Some kind of curve in there like that. So hopefully you got 3 answers that look like that, and I'll pause here in just a second and see if anybody had any questions on that.